All right. Geometry, lesson 39. We'll also be covering lesson 40. First off, we're going to talk about inequalities in triangles. The lengths of each side of a triangle are related to the measure of each angle in a triangle according to theorems 39.1 and 39.2, and you'll see these here in a second. Basically, there's a direct relationship between the size of an angle and the side length that is opposite that angle. The larger the angle, the longer the side that is opposite of it. The smaller angle, the shorter the side that is opposite of it. But you have to be able to look at the connection between an angle and the side opposite. I've had students where I just almost beat my head against a wall because I could not get them to recognize the side that was opposite. So just so that we're kind of establishing this now, okay, now we do understand that in terms of labeling a side, that takes 2 points, right? Okay, so I'm going to label this A, B, and C. And angle A, what side is opposite of angle A? Side BC. Side BC. Does everybody know that? Yes or no? Okay, so let's try another one. That was Michael's answer. He was right. What side is opposite of angle C, Jose? AB. Perfect. Okay. And Chandler, what side is opposite angle B? AC. Very good. I didn't call on everybody, but does everybody get it? All right, because if you don't get that, the rest of this you're going to struggle with it. All right, it shouldn't be a hard concept, but I had students that no matter what I said, you could say angle A, what side is opposite of it, and they would tell you AC. Here's one of the things that you could pick up on. Right, it's an adjacent side. Anytime I have an angle, if the 2 points that represent the side opposite or represent the side, if one of them includes the vertex itself, you know it's not opposite. There's only 3 points, right? So the side opposite is going to have the 2 points that aren't the angle that I'm coming from, right? So if it's B, then it's got to be AC because neither of those letters is B. Does that help? I don't know. Anyway, so getting into theorem 39-1, if one side of a triangle is longer than another side, then the angle opposite the first side, see this is based upon the sides, okay? If one side of a triangle is longer than another side, then the angle opposite the first side, the longer side, is larger than the angle opposite the second side. Think about it this way in terms of right triangles. We've talked about the hypotenuse a lot, right? And if I ask you what the definition of the hypotenuse is, several of you will say, and you're not incorrect in saying, that the hypotenuse is the longest side of a right triangle, correct? It's also opposite the largest angle in that triangle because none of the other angles are going to be greater than 90 degrees. Does that make sense? So the longest side of a right triangle is opposite the largest angle. Okay, so longer the side, larger the angle it's opposite of. Shorter the side, smaller angle opposite. Right, and that's what theorem 39-2 says. It basically says the reverse. If we're going from one angle, if we're looking at angle measures, Jordan, wake up. Come on, stay with me here. All right. I know, but I like to have eyes open. Okay. All right. If one angle of a triangle is larger than another angle, then the side opposite the first angle is longer than the side opposite the second angle. So one tells me, if I know this about the sides, then I know this about the angles. The other one says, if I know this and this and this about the angles, then I know this, this, and this about the sides. Does that make sense? There's a direct relationship between angles and sides of a triangle. In other words, a triangle's largest side is always opposite the largest angle, and its smallest side is always opposite its smallest angle, and then there's only one angle and one side left. Okay. All right. You want to recall way back in lesson 15 that the measure of the exterior angle of a triangle is equal to the sum of the two remote interior angles, right? We could add those two things up, and they're going to be equal to that exterior angle that's outside the third angle. This result leads to the exterior angle inequality theorem, and that basically says the measure of an exterior angle is greater than the measure of either remote interior angle, because it takes both of them to add up to it, that exterior angle is going to be greater than either remote interior angle by itself. You follow me? Okay. It is not true that any three line segments can make a triangle. Only line segments of certain lengths can form the three sides needed for a triangle. Okay. What we're saying is that, yeah, you can get, any three line segments possibly to touch, but the difference is that they may not touch at their ends, right? They have to fit within they have to have a certain quality about them that allows three line segments of certain lengths to touch directly on their endpoints. Excess or shortage. Does that make sense? All right. All right, and that's where we get into theorem 39-4. The sum of the lengths of any two sides of a triangle have to be greater than the length of the third side. Okay. For example, a triangle could not have side lengths of 3, 5, and 9 because 3 plus 5 is not greater than 9. Okay? And it has to be greater than 9. We're not even talking about being equal to. Okay? So let's go ahead and try something out. Let's give me some single-digit numbers. We'll see if these side lengths represent a triangle. Okay, so you got 2, 4. Give me another one. 2, 4, and 6. Okay, so the inequality we would work with is 2 plus 4 greater than 6? No, because 6 equals 6, right? Notice the sum of the lengths of any two sides of a triangle must be greater than. It doesn't say greater than or equal to. So 2, 4, and 6 could not make a triangle. You want to try some other numbers? 3, 5, and 6. All right, so 3 plus 5, is that greater than 6? Okay, good. All right, then we got to try other pairs. 5 plus 6, is that greater than 3? Okay. 6 plus 3, is that greater than 5? Okay, because all three of those statements are true, are there any other combinations that we could come up with? Shouldn't be, right? We should have covered all inequalities. And because all of those inequalities are true, then yes, if I had, let's say, 3 sticks, one was 3 feet, one was 5 feet, one was 6 feet, I could connect the endpoints and make a triangle. Okay? But if one side is too long, say you had a 3, 5, and a 10, they're not going to make a triangle. All right, next lesson, finding perimeter and area of composite figures. This is really fairly simple. A composite figure is where you have like some sort of abstract shape. You would see this in houses, in buildings, right? Not every building is a perfect square, right? And that's it. Your house may not be a perfect rectangle. You got bigger houses where one section of the house, kind of comes out. Maybe it's a circle. Maybe it's a bigger rectangle connected to a different shaped rectangle. You know what I'm saying? Okay? You could see, if you looked at a blueprint of a house or a building, you might see something like this. You could find something like that, couldn't you? And the question would be, well, how do we find the area of something like that? Well, this is a composite figure, okay? And composite figures we can break into smaller polygons that we can find the areas of. There might be a trapezoid attached to a triangle, attached to a rectangle, attached to a semicircle, all making one composite figure. And we can find the areas of those if we take that figure and we break it apart into those shapes and find the area of those each individual shapes and then add them all together. Same way with perimeter, right? We can find those different segments around, right? Solve for them, add up those lengths, right? And get our perimeter. Let's see. So a composite figure is a plane figure made up of simple shapes of a three-dimensional figure, or a three-dimensional figure made up of simple three-dimensional shapes. So we can do the same thing with a cylinder and a hemisphere and a prism or a pyramid. We can attach these things together and find the volume. Okay. Let's see, the perimeter of a plane composite figure is the sum of the lengths of its sides. If two polygons are congruent, they have the same area. The area of a region is equal to the sum of the areas of its non-overlapping parts. Down here you get an example. Here we have, you know, if I got rid of, and I can't, but if I got rid of this line right here, you know, we took that away, it would look more complex. But here we've got that line, so all I would really have to do is find the area of this large right triangle, the area of this smaller right triangle, and the area of that rectangle. Add those areas together, that's going to be the area of the composite figure. Should not be overly difficult, but there's not always just one way to do it. Especially if we have multiple rectangles attached at different points, we can break them up a little bit differently. So it is interesting to watch how different students will break up a figure into different types of squares or rectangles or triangles or what have you. All right, the area congruence postulate and the area addition postulate make it possible to find the area of complex composite figures by breaking them down into simpler shapes and finding the area of each of those shapes, because we have somewhat of a limitation on what we have formulas for. We have area formulas for trapezoids, rhombuses, squares, rectangles, circles, those, you know, semicircles. Like we can find out a bunch of that stuff, but you know, we're not necessarily going to get a formula for an irregular nonagon, right? So I might have to look at how I can break that into smaller workable formulas. All right. All right, so here some of these are already broken apart for you. All right, it says the figure is a square placed on top of a trapezoid. The perimeter of the square is 28 centimeters. Find the area of the figure in square centimeters. All right, I want you to think about this. I want you to look at it, consider it. Just like, I mean, you don't have multiple choices here. So I want to give you a minute to look at it and see what kinds of things that you would do to solve this. Remember, we're trying to find the area. Notice the different kind of markings that are on it. Try to remember what those marks might mean, how we can apply those. All right, look into the question itself. See what information they're supplying you with. All right, if I gave you this as a sheet of paper, I would probably have you underline or highlight certain words that are going to be hints, information that you might want to have. All right, let's look at the reading for a second. The sentence that starts the top of it. Is there anything that you would underline that might be helpful to you in setting up how you're going to work this out? Yeah, Chandler. Okay, perimeter of the square is 28 centimeters. So you're looking at that as important information. Okay, Katie? Okay, so I would probably underline square and trapezoid, right? Why are those two words important? That's what you're trying to, it might, I might need to go back into what I remember about what is true of squares, what is true of trapezoids, right? Okay, what do I know about squares? 4 equal sides, very good. That is important. That's important here, right? And it's going to pair up with what Chandler had you underline, right? We want to find the what of this area. That's something else I would probably want to underline. I'm not trying to find the perimeter of this figure. I'm trying to find the area of the figure. Okay. Finally, we could say probably if this was on a test and I had to label, I'd probably underline I need square centimeters for this. All right. All right, so that gets me through the reading portion of it. Let's look at just the picture itself. Jose, is there anything about the picture itself that you would try to make note of, do something with? All the sides of the square are equal. Okay, good. How do you know that? The line thingies. What do we call the line thingies? Tick marks, right? Okay, so that's true for two reasons. One, they showed that to me visually, right? But they also gave me in the reading, right? They didn't say that this was a quadrilateral placed on top of a trapezoid. They went so far as to be specific to say that it was a square and not a rectangle or some other, they didn't say it was a rhombus, right? They made sure that I knew that that is a square, and I go back to what Katie said, is that all sides of a square are the same length, and then we have these tick marks. But the tick marks, are they only about the square? What else are they about? They show up in the trapezoid, which means if I knew the side length of a square, would I also know something about the trapezoid? What would I know about the trapezoid? I would know the different segments that are represented by those tick marks are the same length as what? The sides of the square. Okay, so let's go from that. I know that the perimeter of the square is 28 centimeters. What do I do with that? Is there anything I can do with that? 28 divided by 4. Why 28 divided by 4? What purpose does that hold? Find the length of the side. And a square has 4 equal sides, so dividing it evenly by 4. Okay, what's 28 divided by 4? 7. Okay, so where do I put the 7? What is that involving? Okay, so 7 there, 7 here, 7 here. Anywhere else? Down here, right there, right there. Anywhere else? Bottom part of the square or top part of the trapezoid. Okay. All right, now I want to find the area of the composite figure. Okay? Is there a formula for finding the area of a square on top of a trapezoid? Or a, let's see, 6-sided figure that looks like this? No, so what might I have to do to find the area here? All right, so how do you find the area of the square? Side squared, and the side is? So 7 squared, right? All right, so we got 49. What about the trapezoid? How do I begin to find the area of the trapezoid? All right, what is base 1? Sure. So what is base 1? 7 plus 14. How'd you get 14? All right, so we're looking at just adding that length. So you're not trying to split this into 2 separate trapezoids then. Could we have? Sure. But then one part of the base would be 3.5 over, plus 7. Okay. What is the height of the trapezoid? 7. And then what do I need to divide that by? 2. Okay. All right, Jordan, what do you do? I mean, they've got the formula for you, but what would you do with it to solve it? Let's say that you got that. All right, so what do you get with parentheses first? 21. Okay. What's next? Okay. 147. 17.5. 73.5. All right. What do I do with that, Maddie? I got 73.5, and I think I got 49 for another part. Anything? Oh, I'm asking you. What do you do? Because when you're taking a test, you don't get to ask the test questions. I don't know, test. What do you think? What did the 49 represent? The what of the square? The area of the square. So they said this was 49, right? What did the 73.5 represent? The what of the trapezoid? The area of the trapezoid. Okay, so 73.5 was here, right? What was the question asking me to do? Find the area of the whole thing in square centimeters. All right, so what do you need to do then? The area of this is 49 square centimeters. You would agree with that? Okay. The area of this is 73.5 square centimeters. You'd agree with that? But I want to know the area of the whole thing. What do you do? Add them together. Very good. All right, what's 49 plus 73.5? $122.5. Anybody going to check that? Confirm it? Centimeters squared, correct? Okay, does this make sense? Okay, and so if you look down at some of these other questions, you'll see that, oh, let me clear. You'll see that there's different ways to break some of this down. If they're talking about square feet, how much carpet will be needed, they're talking about this whole thing. What we could do besides the addition property is could we find the area of this whole thing and then just subtract? We could subtract this square and that square out of it. Could we do that? Yeah, we could do area subtraction, right? We could do 15 plus 7 times 15 plus 7, and then subtract 49 and subtract 49 to get my area, right? Or I could try to do, something like this, right? Get a 15 by 15 and then try to figure out what this would be and what that would be, right? I mean, you couldn't, I mean, is it possible to? Is it the easiest thing to do? No, it's not. Okay, so we're looking for ways maybe not to make our life more difficult. You look at this one, that's a rectangle plus a triangle, but what am I actually trying to do? Perimeter. So it's important to read. Don't just assume I've done area. I'm going to continue to do area all the time. Here I'm just adding 3 plus 5 plus 3 plus 4 plus 3, right? We could probably figure it out, but that would be more of an algebra 3 type of situation where we'd have to solve for that height line. I would say it's probably possible, but you're right. At this level, no, we would not have enough information. Here, and if we're looking for the area of the shaded region, we would find the area of the rectangle and subtract the area of the triangle from it. Does that make sense? Okay, and we could do that a lot easier than, say, trying to, do this where I'm got a trapezoid here and a triangle here and a rectangle there, right? Okay. So there are things that are sometimes subtraction is easier to do than the addition, right? Here, there's a lot of different ways to break this apart, right? I would probably do this. That's not the only way to do it, right? Somebody else may come across here and do that. Okay? Let's see, I'm trying to see. We haven't really... Okay, here's a good one. I want to do this before we're done. Do maybe 2 of these triangle questions. We want to order the lengths of this triangle, of the side lengths, from least to greatest. But what do I need to do before I can start to do that. I need to find angle Z. How do I find angle Z? All right, so you're saying 55 plus 75? Okay, so it would be the same as 80 plus 50. Okay, so you're getting 130. All right, so what is angle Z? 50 degrees. Okay, and we want the side lengths from least to greatest. What it should be the shortest side? Shortest side. Shortest side. Shortest side. How do I identify a side? I can never identify a side as side A. That's not enough information. I have to have, okay. So you're looking at it and you're trying to find the shortest side by what looks like the shortest side, right? That's not what I taught you. What did I teach you? We're not going based upon appearances. The shortest side will be opposite what? What angle? The smallest angle. What side is opposite the smallest angle? Because otherwise, why did we even find angle Z? XY is the shortest side. Does it look like it? No, but that's probably part of the point. All right, what's the next shortest side? YZ, because it's opposite the next shortest angle. All right, and then finally, what is the longest side? XZ. Okay? Do you understand why I was kind of frustrated at the beginning? Okay, because we were trying to look at it. One, we were trying to identify it with one letter, which I think what you were doing is maybe giving me my angle. Okay, last question. Okay, find the range of values available for x. So, this would be 8 plus 3, right, equals 11. Okay, so x has to be less than 11. 8 plus 3, okay? And then 8 minus 3 equals what? All right, so x has to be greater than 5, but it has to be less than 11. Okay, so anytime you get a question like this, it's going to ask you, what are the range of possibilities? I take the two sides, add them together, take the two sides, subtract the smaller from the larger, because I shouldn't get a negative number. Okay, my third side will fit within that range. It can't be 11, right? And it can't be 5. Okay, the reason it can't be, do you guys understand why it can't be 5? Because 3 plus 5 equals 8. Okay, hopefully we understand this lesson. I know I chewed up all of our time, but I want to make sure that we understand it, that we get the concept behind it. Okay, all right, we'll close there.